Okay, so our speaker today is Ken Ono, who is the chairman and Marvin Rosenblum Professor of Math at Virginia. He was in many places previously at Penn State, Wisconsin, Emory, and now UVA. He was vice president of the AMS, had many fellowships, Sloan, BK, Guggenheim, and most importantly, he was math consultant on the movie Man Who Knew Infinity, and he's been in a beer commercial. So.
All right. And where did you go to graduate school?
Oh yeah, he went to UCLA.
Yeah, I got this gift today. Thank you very much. I'm very happy.
Right.
This is why I'm going to a concert tomorrow, but this is really why I came for the hat. So thank you very much. And for all of you, wherever you are on the internet, usually there's a list of participants. I know you're there, but thank you for coming. And yeah, it's lovely to come back. I earned my PhD here almost 30 years ago. Bruce can attest to that. It's just fun being back here. Many things haven't changed. A few things have changed. But yeah, let me talk about some mathematics. It's truly an honor to be here. So this is a colloquium talk. So Terry, this is very different from, well, you might recognize some of the slides, but I'm going to have fun with this. So the lecture I want to give today is called New Results in Arithmetic Statistics. That's kind of an exaggeration. I'm really going to talk about certain kinds of distributions that arise with regard to varieties that are called hypergeometric varieties. But before I get to any of that, I want to start by telling you about a theorem in arithmetic statistics that I could have proven when I was a graduate student here. So I want to make contact with some of the things I first learned here at UCLA. So I, of course, knew about Ramanujan before I ever came to UCLA. My father is a mathematician, so there's a very long story about that. But I was advised by Basil Gordon, who was really an amazing man. He was my PhD advisor here, and he loved Ramanujan. He was a lover of many things academic. And so if there's one thing that you hear from me today, it's that Basil Gordon was a great professor who really raised the level of my experience here at UCLA. And we talked quite a bit about Ramanujan. And I want to talk about an arithmetical statistical result related to perhaps my favorite function called the partition function that might be new to you. The kind of distribution that comes up is probably not new to you, but I like the fact that we're going to be able to prove a theorem along these lines. So a partition of an integer n is any non-increasing sequence of positive integers with sums to n. Here are the three partitions of 3. You count them up. And so the function p takes value 3 at 3. And to give you a visual incarnation of this function, let me shock you. Here are the first few values of p of n. And Basil Gordon actually did something like this with me, not with Beamer or PowerPoint. We pulled out some old articles that Major McMahon had written where oh, Murray, good to see you. Well, that's awesome. Oh, that's great. Where the values of the partition function were listed in 5 columns, and it was quite visual. So this is a different kind of thing. I want you to stare at these numbers. So there's one partition of 0, one of 1, there's 7 partitions of 5, and try to imagine as a data scientist, since that's what's in the air these days, imagine trying to collect some data with regard to the distribution of these values. And if you came up with a conjecture about whatever statistics that you wanted to compute, you would then realize that there's a generating function that captures all of these values at once. So the generating function for P of n is generally described as an example of a meromorphic modular form. So the uniformizing variable for modular forms generally is at infinity. So we let q tau be e to the 2 pi I tau. And this is one of the first functions I studied in a reading course on modular forms here at UCLA. And one of the first things that we studied, given that Basil was a student of Tom Apostol, Tom Apostol had written this lovely book in the Springer GTM series. And one of those chapters walks you through a proof of this theorem, in fact, a much stronger theorem than this. The asymptotic formula due to Hardy and Ramanujan. that says P of n is asymptotic to this rather obnoxious looking function involving n, e, and pi. And I remember talking to him about trying to imagine a more obnoxious looking function. And as a first year graduate student, I had a very difficult time thinking of what would be more obnoxious than this. This is nice, this is obnoxious. Although now in my 50s, this is really quite beautiful and there's a lot of structure in that. So the example I want to start with, just to give you an indication of the sorts of things you might study in arithmetic statistics, is this. The theorem I'm going to prove is not only about the partition function. This is only meant to be a 2 or 3 minute introduction. But imagine writing down the function f of n that captures the first digit of p of n. For those of you who are familiar with my work, you probably know I've done a lot with p-adic modular forms and congruences. And let's admit it, those are like the insignificant digits. What if you wanted to study these significant digits? If anything, you know where I'm going with this, let's define f of n just to be the first digit of p of n. Nothing I say here depends on the base, so that will be, I think, clear as I describe the theorems. But let me show you some data. So just to clarify, the number of partitions of 10 is 42, so f of 10 would be the number 4. The number of partitions of 47 is 37,338, so that first digit is 3. I just want to keep track of the significant digits. And so the question you could ask is, what is the frequency of the possible first 9 values of this function? P of n is never 0, so one of the values has to be one of the numbers 1 through 9. And I see some smiles, you can see where I'm going with this, but I want to talk about the power of modular forms as it arises in this way. So here is a data set. So if you let x be some of these multiples of 10, and you let capital F sub b be the proportion of the first x many values of p of n that begin with b, here's a table. So for x equals 10, 4 of the first values begin with a 1, 2 begin with a 2, and 9 is very lonely. You haven't yet found a partition number whose first digit is 9. By 20, well, it still might look anomalous to you. 7, 35% begin with a 1, and still we haven't found any that begin with a 6, 8, or a 9. And by the time you get to 1 million, something very unusual happens, and if you've never seen this before, this could look very shocking. So it turns out that there is a lot of structure underlying these numbers if you know how to look for them. So what this is an example, a proven theorem. There's this distribution called Benford's law that people really like. It's quite cute. And in this case, there's a theorem that we call Benford's law for P of n. That was a result of some work that REU students of mine did many, many years ago. And what is the theorem? The theorem is as x goes to infinity, these proportions converge to these strange percentages. All right. So it turns out that this is a direct consequence of the Hardy-Ramanujan formula. What's the point? Hardy-Ramanujan tells you that P of n has this obnoxious looking asymptotic. And if you want to study the first digit of a number base 10, like P of n, you're just studying log 10 P of n mod 1. We have a criterion due to Weil that allows you to determine whether certain sequences are equidistributed, which readily applies to functions of this sort. And when you apply this criterion, which I learned also from Basil, you recognize that if you were to plot the points log base 10 of 2, log base 10 of 9, all the way up through log base 10 of 10, which would be 1, you would plot these red bullets. And it turns out that the percentages that arise corresponds to the volume or the length of each subinterval between consecutive red dots. So the partition function is equidistributed with respect to this transformation log 10 base 1, and I think that's very beautiful. Trying to prove this without the theory of modular forms, I don't know that you could even do it. Great. So that is a beautiful example of, I think, an arithmetical statistical theorem that arose from things I learned here as a first-year graduate student, and I was able to give to my REU students many years later. So in that spirit, the takeaway of today's talk is to study perhaps some more sophisticated kinds of distributions as they arise in arithmetic geometry. But the spirit will still be the same. The spirit will be something about the asymptotic properties of various kinds of modular forms And today, the modular forms that will come up are these harmonic Moss forms. So this is very colloquial, so I'm going to leave out a lot of critical details, but the spirit will be very much the same. So if you've never seen the Sato-Tate conjecture before, let me show you how you could discover it yourself. So what we're going to be studying are varieties like elliptic curves, such as the one shown here. And I'm going to reduce them mod p. I'm going to study them over finite fields where the finite field is variant. There's a famous criterion of Hasse, big theorem of Hasse, which is a precursor of Deligne's theorem as part of the Tate conjectures, that says that if p is a prime and you define a of p to be the error term, the difference between p plus 1 and the number of points on your curve over fp, then this integer a of p is small. It's bound and it's required to be in this interval from -2 root p to 2 root p. And what Sato-Tate did, and what you can do too with the help of a computer, is compute lots of these numbers a of p. This is what's called a trace of Urbanience. And if you do that, and you actually normalize a of p by dividing by 2 root p, so that the resulting value is between -1 and 1 to normalize to take into account the size of the field, and make a histogram, or take a screenshot of Drew Sutherland's webpage, what you get is a picture that looks like this. And it wouldn't take you very much thought to recognize, well, this is a distribution, so the integral converges to 1. It's not quite a circle, semicircle, but it's a squash semicircle. And what the Sato-Tate conjecture is that for basically every elliptic curve, those without complex multiplication, namely choose another model, we go through this calculation that the histogram should be a sophisticated way of finding the semicircle. All right, much more easily said than done. So the Sato-Tate conjecture, going back to the 1960s, asserts that if E is an elliptic curve without complex multiplication, and if you define an angle, theta p, to be an interval 0 to pi, satisfying this rule, this is just a reformulation of what I said a moment ago, and you wanted to plot the angles, what they conjecture then is for every subinterval, say alpha beta inside 0 to pi, that if you just take a limit of the proportions, so for large numbers x, count the number of primes p towards the resulting angle is in alpha beta divided by the number of primes, that as x goes to infinity, these ratios, these proportions, converge to this definite integral. Okay. So this was a big theorem. When I was here in graduate school, this was one of those theorems that was off limits. It's actually crazy. If I could give a talk on all the theorems that were off limits when I was in graduate school that are not, like now known. So for those of you who are graduate students, the bar is very high for you guys moving forward for the next 20 years. It is really high. But so Richard Taylor and his collaborators in a series of papers proved this conjecture. And he won the Breakthrough Prize in 2015 for this body of work, which includes the proof of this conjecture. Very hard work. So the aftermath of Taylor's work and others, and that is the aftermath of work that began with Wiles and Taylor-Wiles in the proof of Fermat's last theorem, is that there's this huge edifice of work that intertwines the theory of Galois representations with the analytic properties of automorphic L functions. That's the takeaway. And so what Taylor did was he proved something called potential automorphy for symmetric power L functions, and this is a big thing. So what do we know now? We know quite a bit now. So Sato-Tate, properly fashioned for elliptic curves over totally real number fields, is a theorem. And considering abelian varieties of low dimension, there are some theorems and some conjectures by the work of Kilaya, Drew Sutherland, and others building on these themes. This is a very active field in arithmetic geometry. It's one of those $10 million grants provided by Simons, one of those Simons collaboration grants. This is about as active as areas get. So what I want to do is I want to raise some natural questions going back in time as if I had the opportunity to talk to Sato and Tate about this, because their questions weren't really just about elliptic curves. These were broad mathematicians who built edifices of mathematics. So what they were really thinking about are questions like this. For arbitrary varieties of various types, say, and the situation I want to consider is different. instead of fixing the variety and moving the fields, I'm going to study families of varieties over large fields, which I admit is a different kind of problem and is generally easier. So I want to study distribution of families of varieties over finite fields that have some coherent structure, and then I want the order of the finite field to vary. So what I'm thinking about is I'm going to study some varieties over finite fields. There are finitely many of them of certain type, and as the finite field grows, their total number will grow. And I'd like to know under what circumstances are there guaranteed to be some varieties with some exceptional properties, and proving a distribution theorem would be required to get theorems like that. So along these lines, you could ask questions like, are these distributions generally semicircular? It'll be really bad, right? I mean, right? Wouldn't it be really bad if everything that we did that was hard in arithmetic geometry was to produce the semicircle? So I know that sounds snarky, but there's a point that I want to make about that. And the point that I want to make is that different kinds of varieties give rise to different kinds of cohomology that points to different kinds of distributions, which is a very important point. And you have to be able to see that in the analysis. How exotic can these be? And is there a structural framework explaining these further distributions? So I want to answer these questions for three families of hypergeometric varieties, those that are called the Picard-Fuchs type. And let's see what we get. Now, to be fair to others that I don't have time to go into today, there's a large body of work on these sorts of questions. Okay, so Serre, for example, has a recipe for predicting the kinds of distributions that I will be showing you. And so for those who want to go off in that direction, I don't have the time to explain any of that here, but I want you to be aware that exists. So a picture is worth 1,000 words, at least I hope. And so the takeaway from today's lecture for the three families of varieties I'm going to study is that the distributions that we get fall into one of two types. So if you're familiar with the theory of random matrices, where you can compute integrals of powers of like traces of matrices, the so-called integral moments, it'll turn out that for elliptic curves, the general pattern is semicircular. This is what's called the SU2 distribution. And for a family of K3 surfaces that I want to spend most of the time today talking about, you get something very different, which I like. We call this the Batman distribution. And as a distribution, you integrate from there to there, you get one. But the significant point I want to make is that there's two vertical asymptotes at plus or minus one, which allows us to ask questions that you might not want to ask when you stare at the semicircle. So these are examples of hypergeometric motives. I'll give defining equations in a moment, and I'll give an indication of what we mean by that. And if this is a subject that you're very interested in, this is a very active area. David Roberts and Fernando Rodriguez Villegas have a very nice expository article just from a few months ago in the notices of the American Math Society. And I strongly encourage certainly the graduate students to read the articles and the notices, and this would be one of them. All right, so I have to do a fair bit of hand waving here. So this is really not a definition, but it's sufficient for today's talk. A Picard-Fuchs equation will be a linear ordinary differential equation whose solutions describe periods of Calabi-Yau varieties. Okay, that's a mouthful. So let me explain what I mean by that, because I can describe this all in terms of defining equations. So it turns out, as has been well studied for centuries, that you can write down solutions for large swaths of differential equations using classical hypergeometric functions. So the HFJ class stands for classical, will be an infinite power series in X, whose coefficients are ratios of products of what are called Pochhammer symbols divided by n factorial. At the interface of combinatorics and, well, in the interface of many fields, hypergeometric functions just arise because you can easily write down solutions to differential equations taking advantage of this combinatorial structure. These Pochhammer symbols are called rising factorials, and let me just say that's what they are. So the three families I want to consider, the first two are elliptic curves. And I think one of them is probably very well known to you, might even arise in your complex analysis class. It actually did for me. Ted Gamelin taught me complex analysis. I learned about the P function. It was awesome. And that was the first time I ever heard that something out of complex analysis, a function called J, was like number theory. I'll never forget the day he said that, and I was stunned because there were like no numbers on the board. So the hypergeometric elliptic curves I want to study, the first one's very famous. These are called the Legendre form elliptic curves. They arise many places. And in the context of today's talk, I want to emphasize a very important theorem of Gauss. So for real numbers lambda, appropriate real numbers lambda, for this curve, the real period called omega up to this proportionality constant 1 over pi is the special value of this function. This might not be how you first have encountered this formula before. There are things called elliptic integrals that arise. Gauss's 2f1, or a function you might know as capital K, arise. And this is just a recapitulation of those formulas. Here's one that's much less well known, but the point needs to be made. And so I want to go through this a little bit more slowly than I did with Gauss. In 2010, not that long ago, Gauss was centuries ago, but in 2010, not long ago, Dermot McCarthy, a professor in Texas, proved that for this family called the Clawson form elliptic curve, where the parameter lambda lives here, so this factor is a linear times a quadratic, often irreducible. He proved that the real period of this curve is given by the special value of this function 3f2 up to some other normalizing factor, except it's the perfect square of the period. So when you see theorems like this, you can imagine, well, for certain special values, these curves will be examples of these curves. So maybe there's a theory relating 2f1 functions to 3f2 of some sort of functional equation type. And so maybe there's a rich structure relating families of varieties. And that's the direction that I will be going in. So why is this called the Clawson curve? Because for those who are in the know and for those that don't know, what I alluded to here about a functional equation relating 2f1 and 3f2 exists. It's called Clawson's hypergeometric identity, where 3f2s are related to squares of 2f1 functions. So that's a built-in thing. So the three families I want to study are the Legendre family, the Clawson family, and this third family. This is where I'm going to spend most of my time emphasizing the role of these functions. These are K3 surfaces. If you haven't studied them before, maybe just look at this red equation, and I'm studying these red equations as the parameters lambda vary. So for rational numbers lambda, apart from 0 and -1, for reasons I think you can see related to singularity, I want x lambda to be the K3 surface arising as the function field of this equation. If you're wondering, in number theory, we know about the power of proving that varieties are modular, right? The proof of Fermat's last theorem relies on the fact that every elliptic curve over the rationals is modular. So you might ask, to what extent are these varieties modular? Well, here's the first part of this theorem. It happens, but it's very rare. There are infinitely many rational numbers, but only for the numbers lambda in this set, which I will call SCM, do you get a modular form whose coefficients dictate the behavior of these varieties, mod P and over finite fields of characteristic P by means of their zeta functions. It's very rare. And in fact, that's a general theorem. You can't write down a one parameter family of K3 surfaces and have them all be modular. It's always a finiteness theorem. For all other lambda, these are K3 surfaces with generic Picard number 19. That might not be important for what I'm about to say, although it is important kind of invisibly in terms of the proofs. Maybe I should say a few words about that. K3 surfaces with large Picard number are those surfaces for which the zeta function and a characteristic P. The zeta function encodes the number of points on these varieties in characteristic P over FP squared, over FP cubed, so on and so forth. And when the Picard number is large, it means that the complexity of the zeta function is remarkably simple. And so in this case, it means that there are two eigenvalues of Urbanience that move, and all the other terms are more or less fixed. And that will be very important in my proof. And if that doesn't mean anything to you, I want you to know that this is not a theorem that applies to all K3 surfaces. It's a different picture depending on the Picard rank. So the mantra that I want to teach here, which I also learned towards the end of my stay here at graduate school, is really quite beautiful. And it's not so well understood. There's a mantra that says that for these hypergeometric motives, for these varieties given by solutions to differential equations, it turns out that the hypergeometric functions not only have the property that they give the real periods, the stuff of Gauss and Hartley, but it turns out, and I learned this from Gordon, he told me to read these papers by John Green because it looked like nobody else was a brilliant thing. And he taught me this mantra. He goes, if you write down these finite field hypergeometric functions, which were not so well studied at the time, so classical is now replaced by a red subscript for FQ. It turns out that they're hypergeometric functions where the parameters, instead of being numbers, are characters. They're homomorphisms to the roots of unity. And it turns out that these hypergeometric functions are good at counting points, counting the number of points on the varieties that have the property that their periods were given by these functions. So he asked me to work out some cases. So this paper of Green in the mid-1980s already worked it out for the case of the Legendre normal form curves. At the time, it was already becoming very much something in the air that if you want to study elliptic curves over finite fields, you study Galois representations by modular forms. But he had a point. He had a point that there are other functions that a priori appear to be divorced from the theory of modular forms, certainly very different from the theory of Galois representations. And they turn out to be very elementary to define, that have the property that the number of FQ points on a curve, the Legendre curve, is essentially given by the special value of a single function that is just God-given. So although I didn't do this in my thesis, I saved it. And one of the first things I did as a postdoc is I proved the following theorem for the Clawson curves. Now, you don't see the Clawson curve here, but you do a little bit of algebraic geometry to relate the Clawson curve to the K3 surface. And if you do that, you were able to prove, or I was able to prove, that the number of points over the finite field FQ with the K3 surface given by the parameter lambda is an elementary polynomial in Q, just like the ordinary Q plus 1 or P plus 1. And the error term was given by this 3F2. So the periods are given by 2F1 and 3F2 classical hypergeometric functions. And this mantra that says that there's a recipe for choosing these characters, which I've suppressed from the notation. That there's a recipe for choosing these characters so that these functions count points was quite beautiful. What are these hypergeometric functions over finite fields? They are just extensions of things that you may have already studied. Gauss sums, Jacobi sums, but in a one parameter family. So if you have a finite field FQ star is a cyclic multiplicative group. The A's and the B's are the characters, homomorphisms to roots of unity. And the n(fn minus 1) hypergeometric function has some characters and is a function in the variable x. And it turns out that due to the independence of characters, you can write every function as a finite linear combination of the values over the characters. So you do that. And what are the coefficients? Well, they look like binomial coefficients, but that was John Green's choice. But what they really are twisted Jacobi sums. These are very classical things. If you don't see at first glance how any of this looks like a sum of rising factorials times powers of x, let me just say that if you sit down with a book and study the relationships between the complex gamma function and Gauss sums and so on and so forth, you'll see that there's almost like a dictionary. This reflection law becomes this for Gauss sums. This product of Gauss sums is like a product, right? There's a beautiful dictionary there. And if you study that, then this would make complete sense. So in view of the question, if we want to study these statistical distributions, these theorems take the geometry out of it because it says that for these problems, there are God-given functions whose values dictate these things. And that's a hallmark of these hypergeometric motives. So if you want to study the Legendre normal form elliptic curve, you want to study and reproduce the Sato-Tate distribution in the family, then what you really want to do is just study the distribution of these values. So the counterpart of Haas's theorem appears here. The finite field is of order p to the r, and if you multiply by root p to the r, this always gives you a value, an interval from -2 to 2. To give an indication that we're working and will later be working with hypergeometric functions with more and more variables, I want the length of the interval to reflect the complexity of the function. So in this case, instead of going from -1 to 1, we go from -2 to 2. So this first theorem, this was Green's theorem. The error terms for point counts will really be like studying Sato-Tate for the Legendre normal form elliptic curve. So here is a theorem. And the theorem is a little bit unsatisfying if you were looking for an exotic statement. But on the other hand, if you're looking for some rigidity, some canonical structures related to kinds of distribution, you're quite pleased, because what this theorem said, and this is joint work with my former postdoc, Neelam Saikia, and my current PhD student, Hassan Saad. The theorem says that for any interval AB from the inside -2 to 2, that these renormalized hypergeometric values divided by the order of the finite field, the count of those values that lives in this interval AB converges to the squashed semicircle. So in other words, we haven't escaped anything other than exactly the same description that was obtained by conjecture by Sato and Tate. There's actually a mantra here. If you take any infinite family, any one parameter family of elliptic curves where the J invariant is not fixed, if that means something to you, the theorem is going to be that this is still going to be the semicircular distribution. There's a framework for that. So here's a picture. So if you consider the finite field of order 93,283, count points on all those curves. And my student did this, although I'm sure Drew could have done this, of course, even faster. He's a wizard. You get a picture, and it gives you some indication of how slow the convergence actually must be to semicircular when you see this picture.
Just as a competition, is the hypergeometric function much faster to calculate?
No, it's much slower. Yeah, you mean calculate 2 of 1? Yeah, much slower. Because would you read? Well, x compared to what? Literally counting x equals 0 to 1 to the p minus 1 of the Legendre symbol.
Yeah.
Maybe it's about the same, but they're both slow. Yeah. The way I would use the modularity of elliptic curves and use the fact that we have a recurrence relation, takes the first n coefficients and spits out the n plus first one. Yeah, that would be faster. But that kind of recurrence relation doesn't reveal, for example, multiplicative properties of Heck operators. It's really a statement about certain differential operators on modular forms, right? Okay, that's an interesting point in a different direction. All right, so let's talk about what this means and how we would go about proving this. I won't prove this theorem. I'm going to indicate how you prove the next theorem on K3 surfaces, but it's proven in the following way. So if you consider the compact Lie group SU2, and you compute the even power moments, which means you take the integral over the Haar measure for SU2 of even powers of traces of random matrices X. We know how to compute those moments for every n. We can compute all of these moments, and we get exactly the same formula. And so you automatically get the same distribution. I can't give you, well, so that's how that works. So what about these K3 surfaces? I call them the AOP just because, as many of you might know, it's still an industry to write down exotic families of K3 surfaces with some properties. So I found this K3 surface with my postdoc Scott Algren and David Pennison at the time, and I just figured I'd just call it the AOP. So if we want to study the traces of Urbanience or the distribution of point counts for them, we've transformed this into studying the values of the 3f2 function, where you randomly choose lambda from the finite field fp to the r. And under this normalization, you get numbers in the interval from -3 to 3. And as I mentioned earlier, these are the error terms in the point counts. How was that behaved? And here's a theorem. The theorem is here, but so far has no content. If you choose any interval AB inside -3 to 3, and any fixed shape of finite field, so fp to the r is fixed. So if you only wanted to do fp, r would be 1. But if r is 2, you're taking the limit over fp squared, where p is moving. What we're able to prove is the proportion of these values that lie in the interval a to b converges to this definite integral. So right now this theorem is contentless because I didn't show you f. So now let me show you F. F might look objectionable. This is F. And the first time you write it down, you might say, I really messed up. And in fact, by looking at it, I may have actually messed up. But let me show you what it looks like. This is my Batman. All right, this is Batman. I like it. Do you see Batman? My wife Erica is here. And she named it Batman. I remember she's like, no, it's a Batman. But there's a difference. The curve is meant to outline the actual function. There's two vertical asymptotes here. And so there's a natural question you could ask. What is the rate of convergence? And let me begin to ask those questions. So here's a theorem that my student Hassan Saad just proved. Exactly the same setting, but it's only stated here for finite fields FP. It's a more complicated formula for FP squared, FP cubed, so I don't want to show that. But for the finite fields FP, the difference between these proportions, P is fixed, anything bigger than 5. The difference between the actual proportion, that's a rational number, and this definite integral never exceeds 111 over P to the quarter. And the point is, as P goes to infinity, this is going to 0. So it's showing how these histograms I've shown you must begin to converge to this thing that has two vertical asymptotes, which I like. Because what does it say? It says I can draw this picture for you and just draw, for example, and this is just one example, but I think it's the prettiest one. I can just draw a horizontal line at y equals t. T is some random thing. And then I can ask you, when is a finite field absolutely guaranteed to be large enough so that one of these K3 surfaces has to have a trace of Urbanience living high up in Batman's ears? And as I showed you some of these pictures, you realize that that's an issue. This bound is, of course, not sharp, but it's P to the quarter is pretty good. It goes to 0. It goes to infinity faster than lots of functions that we say still go to infinity. Okay. All right, so I'm quite proud of Hassan for proving this theorem. So this is an example where the analytic number theory combined with the automorphic forms will say, you might have to wait a long time depending on how high T is, but there will be certainly all but finitely many finite fields are guaranteed to have every possible type of K3 surface as dictated by a choice of T. I like that. Great. So in terms of random matrices, how do we prove this again? Well, we prove this again by noticing that there are known formulas for computing the moments, the integral even moments of random matrices from the real orthogonal group. And what we were able to prove directly from the functions is that we get exactly the same moments that come out from the random matrices. There's no map. That would be the dream, but we don't have that. So unlike where random matrices are often used to make predictions, this is a situation where the random matrices gave us a clue of what we were supposed to prove. So this summer, many of you might know I have an REU. If you're wondering, what about the ordinary type of Sato-Tate? When we started, E was an elliptic curve and the fixed elliptic curve and the finite fields were moving. And then I switched. Let's write down a family of elliptic curves growing in number with the finite field, and we turned it into a sampling problem. So you might say, what about the ordinary Sato-Tate for K3 surfaces? Fix a K3 surface, compute how many FQ points or FP points it has, and study the distribution as lots of P's are collected. So that's an REU problem. So Chanlin Chen, a student at Stanford, and where's it, Ryan Chen? Ryan and or Quanlin Chen and or Quanlin or Ryan Chen, I'm really sorry. Together with my former student, Jesse Garner, proved the following. And I don't want to write down these proportions again, but I think you can get what we mean. The K3 surface is fixed. So the horizontal Sato-Tate, where we're sampling many different finite fields, that actually breaks up into two cases, which I didn't predict a priori because I hadn't thought it through carefully enough. But if you look at the defining equations, you would have seen some lambda plus ones floating around. And if that lambda plus one is a perfect square, it actually forces something to not be symmetric. So the distribution folds over to the right-hand side. So it's not always symmetric, but generally is. So our theorem about sampling, where we get O3, is generically what's true, except in these very few but infinite number of special cases, you get the SO3 distribution. So how do we prove all of these things? So I don't want to show you explicit details because you don't want to see them, but let me walk you through the salient points because it's all very concrete. So the problem that we want to study is I'm just studying kinds of finite field hypergeometric functions, and I'm evaluating them at all the possible values of the finite field, and I just want to count how often these values, when normalized, live in specific intervals. So this strategy is well known, I'm sure, to you. You had your course in probability and statistics. It's used the method of moments. So what I want to do is I want to come up with closed formulas for these gadgets that allow me to do some analysis so I can compute asymptotics as q goes to infinity. So there's two tasks here. One, can I come up with an alternative form of this formula for every m? And then we do the analysis. All right, so we can do that. The claimed distributions, I've sort of walked through it already. When you compute these moments, you find that you've actually reproduced the expected values of the nth powers of random variables x as dictated by those random matrices. So I won't go back to that again. So a real problem is, how do you write down a formula for this using some number theory and some arithmetic geometry? And then how in the world do you do asymptotics on that arithmetic geometry? All right. So there are definitely some obnoxious formulas that I don't want to show you. But I'll show you a few. But before I show you those, I'd like to say in words what I'm going to show you, because the words will be much less obnoxious. So we need to find the nth power moments of these functions. So it turns out in all cases, but regrettably, there's many cases with subcases. I'll show you some cases. Turns out that all of these functions are explicit weighted sums of the class numbers that were defined originally by Gauss and Hurwitz, counting isomorphism classes of binary quadratic forms. What are these class numbers? I also learned this from Basil. It seems like I've learned everything from Basil. If negative d is a fundamental discriminant or a discriminant, we let h of minus d be the class number of the discriminant minus d imaginary quadratic order. So if minus d is a discriminant of a number field, quadratic field, this would literally be the class number, the order of the ideal class group. And the Hurwitz class numbers are assembled from these class numbers in terms of inclusion. So if you have a discriminant which is not fundamental, so sometimes I keep the d versus negative d, I drop the minus sign when I'm going to include them in a power series, but this will be discriminant minus d. We're summing over the class numbers of the intermediate orders between O and the maximal order, which is always a ring of integers. And sometimes we weight them accordingly in terms of the number of roots of unity in these orders, or in this case, half the number of roots of unity, because plus or minus 1 is always present. So these are the class numbers I want to study. And what we want to do is show that these class numbers relate to this. So in particular, there has to be a way of relating the order of the field, FQ, to these discriminants in these problems. So I'll have to explain how that would work. So here's an example. When I say R is odd, FQ, Q is P to the R. So think it's FP, like R is 1. Then the nth power moment up to something like point at infinity, which we can ignore, is a sum, a weighted sum of these class numbers. The dependence on the field, FQ, is right here, 4Q. And the S range through integers between plus or minus 2 root Q that satisfy a congruence condition. So the dependence on the field is here. Haas's theorem indicates that these S's, which will turn out to be traces of Urbanience, live in this range. And it turns out that if you just sum up these class numbers, multiply by S to the M, you get the nth power moment. That's a beautiful formula. This is a way, and what does this formula actually say? What this formula is actually saying is that if you write down the moduli space of elliptic curves, by construction, all of the elliptic curves that appear here have at least a 2 torsion point. And what these congruence conditions mean is that you're walking over elliptic curves over a finite field that have a certain subgroup in them. And this is a kind of problem that comes up in arithmetic geometry. What's interesting about that is the nth power moment is just by multiplying by S to the M, and it's quite clean. There are other formulas like this, and let me just say, and so on. But at the end of the day, all of the formulas look like this sort of sum. And these are identities. So how do you see this? It's actually very simple. If you take a course on elliptic curves here, you'll learn about complex multiplication. But one of the fanciest theorems you will learn is that every elliptic curve pretends to have complex multiplication. It's just that the order generally varies with p. So this is a fact that goes back to Doering. And as I said, global complex multiplication doesn't have that, but never mind that. And so what we really end up doing now is that, and maybe some of you caught this when I defined this K3 surface, it's really a compositum of certain specially chosen elliptic curves out of this moduli space. What I really need to do is start counting. So the finite field has order FQ. There's a number of S's I have to worry about. I need to now count the number of isomorphism classes of elliptic curves over FQ with a prescribed subgroup living inside this group of FQ points, satisfying some congruence condition. And this is well known to us. Written down maybe in the most articulate way by René Schoff. And it turns out that subject to the conditions that we require, that the number of isomorphism classes in the case where the group is Zn cross itself is exactly this class number. So class numbers appear many places. In your course in algebraic number theory, it might come up as first studying the obstruction to unique factorization. But in the problem of counting isomorphism classes of elliptic curves, it counts the number of isomorphism classes over a finite field with a certain number of points, that's the S, with a prescribed subgroup. This n squared means Zn cross Zn lives in it. This S means the number of points is Q plus 1 minus S. And this Q means I'm studying the problem in FQ. Every one of these coordinates means something. And when you assemble those ratios in this way, you get this geometric statement. So to prove the 2F1 moment formulas, it's a lot more complicated than this, but this is the idea. For the Legendre family, the Z2 cross Z2 is always there. That's just the statement that the cubic defining it is given in factored form over FQ. That means I can choose n equals 2 in the last formula. I do a little bit of consideration of how many copies of isomorphic curves arise as you vary lambda, but this is a classically well-known thing. If you've ever studied Silverman's book, you might remember in the section on Legendre family, there's something called the 6-to-1 map with some ratios and lambdas. That's all I'm talking about. And you organize them, and you apply Schoff's theorem, and actually everything I want comes out. That S to the M was designed to be the nth power moment. We just had to count how often each of them arose. Awesome. So it's in this way that the nth power moments are explicit weighted sums of class numbers in both the elliptic curve as well as the K3 surface case. For those K3 surfaces that are related to like symmetric squares or symmetric products of elliptic curves, these arguments generalize. So how do we obtain the asymptotics as P goes to infinity? Now this is where the automorphic forms come in. This is where the automorphic forms come in. So there's a very famous modular form of weight 3 halves. It's called Zagier's Eisenstein series that has the property that apart from the obnoxious stuff, if this wasn't here, this wouldn't be very different from my generating function for P of n. The coefficients are these Hurwitz-Kronecker class numbers. So if I wanted to study the asymptotics of them, I study this function. Many of you in analytic number theory might say, just study the Dirichlet class number formula. You could do that too. Okay? And you could probably prove the theorem I'm describing also in that way. But I want to use these because I want to show how these formulas that I've just shown you for these nth power moments are naturally born. Awesome. So what this is, the obnoxious part, is a non-holomorphic function. Q is e to the 2 pi I tau. And the source of the non-holomorphicity is a dependence on y here in terms of the incomplete gamma function. This is just a forgetful gamma function. You don't start integrating until I tell you. What is a harmonic Moss form? It's a modular form that's non-holomorphic, but is annihilated by a Laplacian operator dictated by the weight. So if you have a real number k, this is a hyperbolic Laplacian operator in weight k. And a harmonic Moss form is a real analytic function that behaves like a modular form that is, well, harmonic. So this is not really quite the right definition because you probably are aware I have to worry about growth conditions, so on and so forth. But If you want to learn about that, I invite you to get this book. By the way, I'm really proud of this book because when I was vice president of the AMS, I asked that it be made free to all members of the AMS. If you try to buy it, like at Amazon, it's $100. If you buy it, sorry, but you can download this for free. I'm very happy with that. All right, so I needed to do asymptotics on those very strange weighted sums of class numbers. So let me tell you, we weren't the first to invent that problem. Eichler, way back, proved a formula for these sums of class numbers. If you sum over S's in some range that replicates the kind of ranges that we want to study, as a function of n, you get a simple function plus a divisor function. And so the idea, and this is not quite what Eichler did, but it's not difficult to explain. The idea of this is, well, what Eichler essentially wrote down without having the benefit of Zagier's function. Right? Zagier's function had these class numbers as coefficients. What Eichler essentially did without having the benefit of Zagier's function is he computed the coefficients of the formal product of Zagier's function with the classical theta function whose coefficients are supported at squares. That's what this n minus s squared is. In principle, that's what he's doing, but of course, strictly speaking, isn't what's working. But if you use this as the idea and recognize that I need to write down formulas like this, but there's an s to the m out here, how would you do that? How would we do this? Right? If this wasn't here, this is essentially what Eichler had, minus the congruence conditions. But so the real thing is how to get this. And this is where I'm very happy, because the theory of harmonic Moss forms is designed, and from many perspectives, was designed to study exactly this question. So how do you deal with the s to the 2m factors? Well, it's easy. Zagier's function is still there. Where does the s to the 2m come from? It's by iterating, taking higher power derivatives on the theta function. Now, unfortunately, differentiating modular forms doesn't preserve modularity, dramatically destroys them. And so you might think this isn't possible, right? This is an argument that you would write down from formal power series, but no, it's totally correctable and exactly in this setting. So this is a mild extension of what Rankin and Cohen did. For those of you who've had a first course in modular forms knows that when you destroy modularity by differentiating, it's not like you've destroyed it by something you can't understand. The obstruction to the modularity is an expression you can control. And if you're willing to go through the exercise of controlling iterates of these error terms under differentiation, you might come across this differential operator. It's a pairing. So if f and g are possibly non-holomorphic modular forms, for every non-negative integer nu, you can consider this formal combinatorial product of products of pairs of derivatives. And what this combination is it's awesome. If f and g are modular, independent of the fact that they might not be holomorphic, the obstruction to modularity is exactly canceled out by this magical combination of signs and binomial coefficients. Great. So you can imagine now where my s to the m is going to come from, because I want to write down some even power derivatives of theta where r is 0. So at least I can write down generating functions that include what I'm looking for as a sum. So this is where I'm going to punt, read my paper. That's not so easy to do, but you can do it. So I gave you the idea of what we achieved. So after a lot of work, what we recognize is that we want to take the Rankin-Cohen brackets, all the even powers of them, where s is 2m, of Zagier's function with these two classical theta functions, one due to Jacobi and the other one due to Jacobi. Jacobi like knew them all. These are, of course, non-holomorphic modular forms with very weighted, ugly, messy weighted class number sum coefficients. But what I want to say is that first, we know how to project these very messy modular forms into spaces, finite dimensional spaces of classical modular forms, very powerful. And we know how to control the asymptotics of the forms that we get under holomorphic projection to the coefficients that we started with. The error term is very, very small, which is really what Hassan Saad did in his most recent work. really make tight bounds on that. And this is kind of a joke to put this in a third bullet point, because if you really write down some of those ranking cone bracket operators, there's a lot to keep track of, and I'm basically keeping track of one term every time, but you can do it. And if you do it, so that's what carefully tease out, you'll get exactly what I want in terms of the moments. To prove the theorem, it boils down to the usual things in the theory of modular forms. Can you find the right Eisenstein series? Can you do some decomposition generically in spaces of cusp forms, and maybe insert some bounds for L functions to make sure the stuff that we don't want interfering becomes just part of the noise. So let me conclude with that. If you do this, you can prove the most complicated formula in the universe for the Catalan numbers. So if the joke is Catalan numbers appear everywhere, you know you've done something right, where at the end of the day, I get the Catalan numbers, which is the hallmark for the moments for Wigner's SU2 distribution. What is typical hallmark for power moments of hypergeometric motives? They're just weighted sums of combinatorial copies of the Catalan numbers. That's another hallmark of what it means to be hypergeometric. And so in the case of our K3 surfaces, there's just a longer sum up to the index of the moment. And if you prove all of that, you get the theorems that I claimed, which, oh, I don't have the picture. Oh, which then is this. And if you learn the standard techniques in analytic number theory, you can get those kinds of theorems, not essentially effective, utterly explicit. Super, and that's all I wanted to say about that. I'll answer a question. I hope everything is beautiful. Yes.
This is a beginner question. When you define those weighted class number sums.
Yeah.
I mean, for imaginary quadratic orders, there aren't that many roots of unity, right?
Oh yeah.
I mean, is that just to make it look prettier, or is there like a deeper reason?
There's a deeper reason. Yeah, there's several different. One is the argument principle. Have you taken a course in modular forms? You look at fundamental domain, right? I isn't in it. Only the top half of I is in it by the argument principle. But there are many other reasons, but yeah. Robert.
Ken, that was such an awesome talk.
I have a ringer in the audience.
I'm not really a ringer. Okay. Number one, this Batman distribution, is that something that shows up naturally in other ways?
Yes, it shows up naturally as from the real orthogonal group O3. So what we'll prove is that the even power moments are exactly those truncated sums.
Oh, I remember. I remember you said that. I'm so sorry. Okay.
Yeah.
Okay. With those types of theorems, you had the bounds A and B were between -2, I think, and then.
Yeah. So
if you expand those bounds, what happens? Do you pick up more, like?
Well, no, everything.
Or that's it.
That's it.
Everything. So is there no cool thing that happens if you expand them more?
Well, there's nothing to prove it. But yeah, so the first theorem you have to prove is how to properly normalize to get a distribution, right?
Oh, okay.
Right.
Okay.
So it's like Deline's theorem.
I got it.
Actually, here's the funny thing. It's hard to impress people with Deline's theorem when you talk about bounding Fourier coefficients until you say compute some and you realize they're really smashing up in absolute value on what's allowable. So getting the exact size is important for knowing how to normalize to get a distribution. And what I have to do here is certainly nowhere near as complicated, but that's the first step. In the hypergeometric variety, you have to do the desingularization and find hyperplanes and so on to get the polynomials in Q. And then you want to compute exactly what the right range is so that when you divide, you get statistics that are independent of the field.
Oh, that's
And
the
that's
game.
what you have to do.
That's so
Well, that's
cool.
a game in every distribution,
Yeah,
right?
I see. Okay, okay, that's awesome. Can I ask one more really fast question? Your F function, the difference, the first term of the partition function. What's the is there something special about the first difference of that? How does P of n to P of n plus 1? How does F of P of n minus F of P of n plus minus
Well, consecutive, you could do that.
Yeah.
Remember, so at the end of the day, when I talk about that being P of n, what I'm really talking about are functions of polynomial type times exponentials in n. So that theorem would apply generically to that. And understanding the difference between n and n plus 1 and like 1 over n e to the pi root n is very easy.
I see. So it's the partition function falls into the category of functions that works nicely for.
Yeah.
I see. That's awesome. Thank you so much.
Right.
Thank you.
So that's why I had this long table out here where I wanted you to stare at that.
Mhm.
And And if you look carefully, so there's a whole lot of ones, but you realize that substituting in for n and then substituting n plus 1 is not a very complicated thing.
Thank you.
But if you've never seen it before, yeah. Yes.
Just another question. So you're saying you're looking at some specific families of elliptic curves and specific family of K3 surfaces. Maybe you kind of already said this and I missed it.
So I really want to be more precise than that.
Yeah.
What I'm saying over here, if you have any one parameter family of elliptic curves with non-fixed chain, with non-constant chain invariant, this is your picture. By the way, you can reprove that, and it's already morally in the literature going back to Katz and Sarnak in their big book on random matrices. And that won't be a surprise. Yeah. Now, if you want to study other families of K3 surfaces, and I know some people are beginning to do that, yeah, you get different pictures. Very different pictures.
Do you get different hypergeometric functions?
You do. But they're easy to find when you write down the right differential equation. You just literally change the classical hypergeometric function, which encodes special properties of the Abel-Jacobi map into some finite field things. And almost always, if there's a parameter of a half, replace in this field, you put the order 2 character, just the quadratic residue character. What if the parameter is a third? Oh, well, I have to deal with FQs where Q is 1 mod 3 to get an order 3 character. And then you have 2 choices, and then you have to make sure the Galois conjugates work right. But they're natural rules that, yeah, are generally easy to guess. But it's a mantra. I can't prove to you why any of it ever works.
It's like just a philosophy that appears that works.
Right. And this philosophy, like I said, it's not mine. It's in the air. Certainly Dwork proposed this in many of his works, maybe not written the way I'm describing it. Koblitz and Gross, of course, right? Gross understood how together with Koblitz the importance of this p-adic gamma function, where in a sentence, the Gross-Koblitz formula is a statement about what the gamma function should be in the world of p-adics. Yeah. Yeah.
Very, very interesting.
And so it's an interesting thing. If you are a concrete person like me, you can almost just go through like a book on special functions and say, what should this be in finite fields? And what does it say about zeta functions? What does this say about zeta functions? And honestly, that's how most of this started.
So cool.
Yeah.
That's all. That's what you were doing?
That's
You were
what-
searching through special
No. Don't tell NSF. No one was spending all this money buying these old books. All right.
Okay.
I don't know how to get any questions if there are any from the audience. I saw Richard Ellman in there. Thank you, Richard, for failing me on my PhD algebra exam.
You used that as a good example for me when I failed my PhD algebra exam. So thank you. I did it. I could do it.
Great. All right, great, you guys. Thank you very much.